Hello, welcome to Econometrics Melody. In this video, we'll discuss about the Laplace distribution. Before that, let us see some of the useful functions. The first is about exponential, deriving the e to the power, the value, required value. E to the power 0 is equals to 1, and e to the power 1, this is the Euler's number, e to the power 1, and e to the power minus 1, e to the power 3, 12, and so on. E to the power minus 12 is this small number, nearly 0. Now let us see another useful function, natural logarithm. The natural logarithm, the base is the Euler's number itself. So we cannot find the natural logarithm of 0, it is undefined. Natural logarithm of 1 is 0, and the natural logarithm is 2. Natural logarithm of 2 is 0.69. And this is the Euler number itself, so natural logarithm of the Euler number should be 1. It should display 1, and the exponential and the logarithm are natural logarithm, they are inverse to each other. That is why we get the same value whatever input we have provided. Again, is the exponential and the logarithm are inverse to each other, we get the same value, and in this case we should get the value of factorial 5 and gamma 6 respectively. Now let us see some of the formulae of Laplace distribution and explain it. Laplace distribution is also called as the double exponential distribution, and which is clear by this 2 CDF, and the mean and the variance of the Laplace distribution is m and 2b square respectively. So the PDF Laplace distribution is again a continuous distribution. That is why we can calculate the PDF. PDF is equals to 1 by 2b e to the power absolute form x minus m. M is the mean, or we can call it as a location parameter, which helps in shifting the location, divided by b. B is the scale parameter, because for our variable x, when we divide by something, we get the scale, that is the scale parameter, and the location parameter, it comes in the form of deviation. So either in the case of PDF or in the case of CDF, we want to ensure that we get e to the power minus something. The absolute term of x minus m is going to result some positive value, and finally we get the minus value, e to the power minus something. Similarly, if we see at the CDF as well, when x is greater than or equal to m, this is some positive value, and ultimately we are going to get e to the power minus something. And here, when x is less than m, this is again negative, and we get the e to the power minus something. CDF is very simple. For x is less than or equal to m, the mean or the location parameter, we calculate the CDF by taking half, 0.5, into e to the power minus x minus m. M is the location parameter, divided by b. X minus m divided by b. This is going to give us a feel of a normal distribution, which we'll explore in other videos. And when x is greater than or equal to m, we calculate the CDF by 1 minus half e to the power minus x minus m divided by b. We'll calculate both the PDF and CDF for each of the cases in our example, and let us proceed towards it. Now let us calculate the CDF by using both the formula. This is Laplace, this is the Stata function to calculate the CDF for the parameter m, b, and x, while this is the formula when x is less than equal, when x is less than m, we have this formula, 1 by 2 e to the power x minus m divided by b. So both of them should yield the same result, and the value of x here is 2, while the value of m is 3. So we get nearly 41%. If we look at here, both of them have the same value, and it's nearly 41%. Now let us say depict it in the graph. So Laplace CDF is a user written program which takes the parameters m and b, and it draws the CDF for the m ranging from 1 to 3. And let us see what does it look like. 1, 2, and 3. M is 3, 1, 2, and 3. So the mean parameter or the location parameter is simply going to help us shift the CDF. And our x was equals to 2. It was nearly 40%, somewhere over here. Now let us see another example in which x is greater than m. So here x is 9 and the value of m is 6. In this case, we use the formula 1 minus 1 by 2 e to the power minus x minus m divided by b. Let us see what is the value. So the probability is 82%, nearly 82%. And let us check it. So here the CDF, we are going to get the CDF from 1 to 6. We are going to get the 6 CDF ranging from 1 to 6, and we will see it for the value 9. It was 82%. For 9, the x to 9, what is the value of CDF? It is somewhere over here, and this is ranging somewhere 80 to 82%. We can draw the CDF of Laplace distribution for any parameter m and b. So in this case, the value of m is 9 and the scale parameter is 30. The scale parameter is going to increase the variance, where mean parameter or the location parameter is going to shift the graph towards the right. Now let us see some of the examples of the PDF. The Laplace then, this is the Stata function to calculate the PDF of Laplace distribution for the parameter m, b, and x. And this is the generic formula for that: 1 by b into e to the power minus absolute term of x minus m divided by b. Both of them should yield the same value, which is equals to nearly 8%. And let us see it by the help of graph. For x is equals to 2, which is nearly equals to 8%. Somewhere over here, 8%. Now let us see another example where the value of m is 6 and the value of b is 3, while the value of x is 9. And from both of the formulae, we need to get the same value. It is nearly 6% for x equals to 9. And let us see it for x equals to 9. For x equals to 8.75, nearly 9, and we get this value. And at the backdrop, we have a normal distribution with the mean and variance equal to the mean and variance of this Laplace distribution. Now let us see another example in which the value of m is 4 and the scale parameter b is equals to 10. And let us see what does the PDF look like for these parameters. Now let us draw the PDF of Laplace distribution for different mean ranging from 1 to 12 and the scale parameter b in a single graph. And let us see what does it look like. As the value of m or location parameter increases, the graph simply shifts towards the right by the same unit. Now let us reinforce this concept by increasing the value of m, or the mean parameter or the location parameter, by increasing it from 20 to 30, and for the scale parameter 10. As we are manipulating the mean or location parameter, the graph simply shifts from left towards right by the same unit. Now let us change the scale parameter and see what is the nature of the graph Laplace distribution. What does it look like? So for the mean parameter m, or the location parameter 1, and we are going to change the scale parameter from 1 to 10, and let us see what does the graph look like. Now let us repeat the process for m to be 3, and the scale parameter b is going to increase from 12 to 21. As the scale parameter increases, the variance of the distribution also increases. Now let us see the area graph of the Laplace distribution. This is useful for hypothesis testing. First of all, the Laplace distribution is symmetric at m equals to 0, or location parameter m equals to 0. And let us see it for the value of b to be 3, scale parameter to be 3, and x is equals to 0. So this is the graph. We have 50% area on both of the sides. This indicates that both of them are symmetric. 50% area towards the left and 50% area towards the right. For the same, m to be 0 and b to be 3, and let us calculate the value of x to be minus 4, and another example, x to be 4, and let us see whether they are symmetric or not. First one, x is equals to minus 4, and let us see what is the area. For x is less than minus 4, we have 13% of the area, and x is greater than minus 4, it is 86% of the area. And let us see whether this will be true for the value x is equals to 4 for the same parameters. Now x is greater than equal to 4, it is 14% and x is less than 4, it is 87%. They are symmetric for the value m equals to 0. So now let us explain the hypothesis testing. Only one tail test. And the Laplace area, this is the program written by Econometrics Melody. We have written it. And for this default value of m to be 3, b to be 6, location parameter or mean parameter to be 3, and scale parameter is 6, we are going to test whether x is equals to 12 is null hypothesis, and alternative hypothesis x is less than 12 or x is greater than 12. For this alternative hypothesis, the area is 89%, just towards the left of this line. So in this case, we fail to reject the null, and we conclude that the value of x is equals to 12. And x is greater than 12. For this alternative hypothesis, again the area is greater than 5% or alpha value. So we fail to reject the null in this case as well. So in both of the cases, we fail to reject the null, and we conclude that x to be 12. Now let us see another example where when the mean parameter is 0 and the scale parameter is 9, we want to test the hypothesis whether x is less than 30 or greater than 30. So this is the Laplace distribution, and we want to see our null hypothesis x is equals to 30. The alternative hypothesis, either x is less than 30 or x is greater than 30, depending on the situation or according to the nature of the question. As we know this, we need to calculate the CDF and PDF of Laplace distribution. This calculation of this value, it should be very easy. X is less than 30 is actually the CDF. So x is less than 30, the p value, it is greater than 5%. Actually it is 98%. That is why we fail to reject the null in this case. For this alternative hypothesis, x is greater than 30, the p value is 2%, which is less than our alpha value of 5%. That is why we reject the null in this case, and we conclude that x is in fact greater than 30 for this alternative hypothesis. Now let us see another example for the mean to be 10 and scale parameter b to be 3, and we want to test whether x is less than 4 or greater than 4. So in that situation, whether we reject the null hypothesis or we fail to reject the null hypothesis. So our null hypothesis, x is equals to 4. Two of the alternative hypotheses, x is less than 4, it is 7%, and x is greater than 4, it is 93%. 93 and 7, they add up to 1 in continuous distribution. Both of them should add to 1. So in both of the cases, we fail to reject the null, and we conclude that the value of x is in fact 4. And let us see another example for the mean parameter or the location parameter -1 and the scale parameter 2. We want to test whether x is less than or greater than 5, depending on the situation or the nature of the question. So this is again a Laplace distribution with the given parameters m-1 and b equals to 2. As m is equals to -1, the Laplace distribution is centered at -1. Our null hypothesis, x is equals to 5, and our alternative hypothesis is either x is less than 5 or x is greater than 5, depending on the situation of the question. So in this case, when x is less than or equal to 5, we see that 98% of the area is covered. So we fail to reject the null in this case, and we conclude that x is in fact 5. But for this alternative hypothesis, x is greater than 5, we say the p value to be 2%, which is less than our alpha value of 5%. That is why we reject the null. X is not equal to 5. In fact, x is greater than 5. At the backdrop, we have the normal distribution with the mean and variance equal to the mean and variance of the Laplace distribution. Now let us see some of the uses of the Laplace distribution, and I've collected it from different sources. Laplace distribution is used to model noise in signals because of its fatter tails, which can better capture extreme values. Similarly, Laplace distribution is used in Bayesian smoothing, which is the technique for estimating the underlying trend in data with noise. It is also used in the study of stochastic processes, which are random systems that change over time. It is also used as a prior in Bayesian machine learning, particularly in linear models such as linear regression and logistic regression. Laplace distribution is also used in image processing to detect edges in image as the Laplace of an image as the Laplacian of an image is a measure of the rate of change of intensity, and Laplace distribution is also used in many other fields, including statistics. And before we wrap up, let us say something about the log Laplace distribution. First of all, we are going to show the PDF of log Laplace distribution, and when the mean parameter m is 1 and the scale parameter is 5. This is the PDF of log Laplace distribution when mean or the location parameter is 1 and the scale parameter is 5. And let us see another example. Now we are changing the mean parameter to be 12 and the scale parameter to be 20, and this is the nature of the PDF. Now let us draw the PDF of log Laplace distribution for different scale parameters. The mean parameter, it is 0, so the graph should be centered at 0, and we change the scale parameter b from 1 to 6, and let us see what does it look like. So as the scale parameter increases, the variance of the distribution also increases. Let us reinforce this concept. Let us center the graph or log Laplace distribution at 0, and we want to change the scale parameter from 7 to 15. Again, as the scale parameter increases, the variance of the graph it increases. So this is it for this tutorial. Thank you very much for your time. Thank you very much, Econometrics Melody.